Hello. Today I will be presenting to you the work that we've been doing this year at University Abdelmalek Essaadi as part of a master thesis, which is about the identification of solar cell parameters using differential evolution. Let's get started. So the importance of accurate solar cell modeling cannot be understated due to their wide range of uses and applications. The two most common models that are used for photovoltaic solar cells are the single and double diode models. The double diode model is precise but incorporates 7 parameters, which increases algorithm complexity. The single diode model, despite its simplicity, provides more than adequate precision in most cases. The goal here, in both cases, is to identify the parameter values that allow us to best fit the experimental data for a given cell or module. Let's talk very briefly about differential evolution. It's a relatively recent evolutionary optimization method. It has the familiar population initialization, mutation, and crossover techniques that you may recognize if you're familiar with evolutionary optimization methods. The diagram on the right here shows the mutation operation, which uses a differentiating scheme, which is where the name differential evolution comes from. So as part of the master thesis, we wrote an implementation of the method in the Python programming language in order to perform our calculations. In this specific example of a 36-cell polycrystalline module, we can see that differential evolution fits the experimental data very well. And the graph on the right here shows the deviation from experimental data through each iteration, which shows us that convergence occurs at around 50 iterations roughly. We were able to validate our code and compare with other implementations using similar techniques on the same solar modules and cells. This table compares the parameters and performance that was yielded by our code against similar techniques in literature. Each technique's deviation from actual experimental data is quantified by the root mean squared error here, which tells us that differential evolution is slightly more precise than the other techniques. So every evolutionary algorithm has a set of control parameters which affect its behavior and convergence. Two of the most important ones in differential evolution are the mutation factor F and the crossover rate CR. There are a few recommendations and guidelines in literature that generally lead to good results, but these are by no means universal, and one may need to build experience by resorting to trial and error. This is because there have been plenty of instances where the best results were obtained by parameters that do not fit these recommendations. A method that we propose to get around this issue is meta-optimization, meaning we'll use differential evolution on a higher order to optimize our standard differential evolution. This results in higher time complexity, but since we're only optimizing 2 parameters, the higher order search space dimensionality is not significant, which allows us to use a minimal number of iterations. So these are the convergence curves associated with a commercial solar cell with and without meta-optimization of differential evolution. The curve on the right is obtained using the recommended control parameters in literature, yet we can see clearly a significant improvement in terms of convergence speed using optimized control parameters. This is the same comparison, but in this case for the previously mentioned 36-cell polycrystalline module. Again, we see an improved convergence speed, in this case within 25 iterations. So we know that standard differential evolution is on par with, if not slightly superior to, the other state-of-the-art techniques for the estimation of solar cell parameters, but we introduced a meta-optimization technique and successfully improved differential evolution, specifically in terms of convergence speed. We should note that the time penalty that is accrued in the initial execution that allows us to find the optimal control parameters is compensated for by the improved convergence that is yielded in subsequent runs, assuming the IV characteristics do not change drastically between runs, of course. In fact, in applications involving a significant number of runs, the time penalty can become practically negligible as it's only scheduled in the first run. Thank you.